Let's continue our mission to Tiangong-1 by analyzing a couple different aspects of the Falcon 9 rocket. Today we're going to talk a little bit about the fairing deployment. Then you'll independently work on the first stage landing and the second stage engine cutoff. If you have any extra time, you can complete all mission profiles from this week. Everything from this week is due at the beginning of the period tomorrow. Anything that's not finished in class today is part of your homework. As you work today, Mr. McNear has answers, so as you finish problems, check your answers with him. If you're struggling, try the problem and then ask for help. Mr. McNear can help you by working off your errors to help you understand and master the concepts. Turn to yesterday's worksheet and find the fairing deploy mission. The fairing is the protective shield that goes around satellites and other space equipment. Once the rocket's in space, the fairing deploys. It falls to the ground like a horizontal projectile. Let's watch some footage of a SpaceX testing its fairing. The two halves of the fairing come apart to release whatever's inside of the second stage. This test was done in a vacuum chamber, but in real life, these two halves would fall to the ground to be caught by a ship in the ocean below. To help figure out where the boat that catches the fairing needs to be, we can analyze the fairing halves as if they were projectiles traveling as horizontal projectiles. There's a couple things we know about horizontal projectiles. The vertical initial velocity is always 0 meters per second, and then we know both accelerations. Vertically, these two halves are falling an acceleration of 9.8 meters per second squared, because gravity is the only thing acting on them. Horizontally, 0 meters per second squared, because they're moving at a constant velocity if we ignore air resistance as they fall back into the atmosphere. All horizontal projectile problems start with these three assumed givens. And again, these three assumed givens we can always explain using our understanding of dynamics, or the forces that cause motion. We're given some other information. For example, the Falcon 9 is moving at 1,240 meters per second when it breaks apart, or when the fairing breaks apart. So that means the fairing is moving horizontally 1,240 meters per second. I only have one initial velocity that was blank, and I double check that my variable velocity matches my unit meters per second as I organize my given information. The fairing falls to the ground from a height of 223,000 meters up. This is a height. This is a vertical distance. So it's a vertical given information. I always make sure that my variable distance, x, matches my unit, meters. Now that I have all of my given information organized into vertical and horizontal information, I can find the proper equation. The first question asks us to find how long it takes for it to hit the boat below. The boat's name is Mr. Steven. So we need to find time. Horizontally, I only have two givens. I need three givens when I'm talking about kinematics. So I have to use my vertical information. My final velocity is not included. When final velocity is not included, I'm going to use this equation. We don't have a version of this equation where time is by itself, so I know I'm going to have to treat this like an equation and use my inverse operations to solve. So step 1, I organized my givens. Step 2, I found my equation. Step 3, I'm going to plug in my given information. I'm finding the vertical time, so I need to use my vertical givens. My vertical distance or height is 223,000. My vertical acceleration due to gravity, which is a vertical force, is 9.8. And my vertical initial velocity is 0, one of my assumed givens. When dealing with horizontal projectiles and solving their equations, look where the 0 ends up. 0 times t is just 0, so I'm left with just half the equation. Half of 9.8 is 4.9, always. So in this case, we always end up with 4.9t squared equals our distance. So I'm going to divide both sides by 4.9, because if I look at this problem, I'm squaring t and multiplying by 4.9. So I need to do the inverse in the inverse order. So I'm going to divide both sides by 4.9. A little calculator moment, 223,000 divided by 4.9 gives me 45,510.2. To undo squaring, so t squared, I take the square root of both sides. The square root of 45,510.2 in my calculator is 213.33 seconds. If you still are unsure how to take a square root in your calculator, make sure that you ask today. We now know the vertical time, 213.33 seconds. I know it's the vertical time because I used the vertical given information. I stayed in that vertical column the whole time. Now, time is the only thing that crosses from one column to the other. If the fairing hits the ground 213.33 seconds, it hits it both vertically and horizontally. So make sure as you find given information, add it to your organization of given information. Once we have that horizontal time, we have 3 givens in our horizontal column. Once we have 3 givens, we can always find a fourth. So let's find the horizontal distance, or in this case, how far the fairing fell. Think about it this way. If you were driving the boat, you would need to know how far to drive. If we know where the fairing drops, we know or can predict how fast it'll be moving, we can decide how far it'll travel horizontally. Final velocity is not included, so I'm always going to end up using this equation. Well, almost always. I'm going to plug in my horizontal information. I want a horizontal distance, how far it traveled horizontally, parallel to the boat that's driving below trying to catch it. So I'm going to plug in all that info. My acceleration is 0 because it's moving at a constant velocity. Time is 213.33. The initial velocity is 1,240 meters per second because that's how fast the second stage was moving horizontally when it dropped the fairing, and it travels for 213.33 seconds. When dealing with horizontal projectiles, always look for the 0. I see a 0 in the first half of the equation. 1/2 times 0 is 0. 0 times 2.33 squared is still 0. So I really only am focused on the second half of the equation. 1,240 times 213.33 seconds. Multiply those two together, and you get a distance of 264,529.2 meters. This means that Mr. Steven, the boat that catches the fairing, needs to be about 264,529.2 meters ahead of where the fairing is dropped. Although it's never actually caught a fairing yet, here is the boat, Mr. Steven, that's designed to carry this or catch this giant fairing. The fairing is big enough to hold a bus, so it needs a net big enough to catch a bus. We've discussed the fairing deployment. Now you're going to look at the first stage landing and the second stage engine cutoff before you finish all of the other mission profiles. But first, let's look at the first stage landing and second stage cutoff a little bit more. Here are some videos of early SpaceX landings or crashings. So just like learning the physics of rocketry, actual rocketry is more of a growth mindset. You keep getting better and better and better until you've mastered the skill. Nowadays, SpaceX can land their rockets almost consistently, whether it's on a drone or on the ground, like this example here. To help prep you for your independent practice problems, let's answer a few finger voting questions. Now, I'm not there, so this is kind of on your honor system. Mr. McNear is watching, as is Santa Claus. Also, I truly trust that you'll all tattle on each other if you don't play along today. As the first stage comes to a stop on the landing pad, which direction is the net force acting? Or in other words, which direction is the bigger force acting as it comes to a stop? Think about the answer. Throw your fingers in the air. Gravity's pulling down on the rocket, and the rocket is applying a thrust force upward. Because it's going downward, but slowing down, it's accelerating upward. The bigger force is pulling up. This is why it eventually comes to a stop. If the bigger force was in the same direction as the motion, the rocket would be speeding up. If the direction and the big force are against each other, the rocket slows to a stop safely, or in some cases, like we saw, not so safely. Assuming we're using this force diagram, where the thrust force is large, the gravitational force is smaller, and that thrust force is unknown. We don't know it, so we can't use the number. How would you find the net force acting on the first stage? You know the mass and the acceleration of the rocket. Which method would you use to find the net force? For those of you holding a 1 up, if we knew both forces, we could subtract them, since the net force is the difference, or the value we get when we subtract our two opposing forces. In this case, however, we can't subtract them, so we have to use F net equals mass times acceleration, Newton's second law. For the second stage, it's going to accelerate from 1,180 meters per second to 8,000 meters per second. If the second stage covers 11,812,754.72 meters in this accelerating time, how long was the engine burning? So we're looking for time. Which of these sets of givens represents this problem that you'll be answering in moments? You'll notice that number one is asking for time, but it has the initial and final velocities confused. Number two is asking for acceleration. We need number three, where we start out slow, end up fast, and it's looking for time. You'll notice in this problem, the second stage has to speed up to 8,000 meters per second. What's important about this speed? Why does it need to speed up to about 8,000 meters per second? This speed is much slower than the speed of light, much faster than the speed of sound. This is orbit velocity. Around 8,000, a little slower, a little faster, and you'll stay in orbit. Much slower, you'll fall to the ground. Much faster, you'll shoot up out into space. After the second stage's engine cuts off, it travels in orbit at a constant velocity. Vertically, there's gravity, but horizontally, there's nothing. Are its forces horizontally balanced or unbalanced? They're balanced because it's moving at a constant velocity and because in space there's no air resistance. There's nothing pushing on the rocket. There's no thrust. There's nothing pulling back, nothing pushing forward, only gravity keeping it in orbit.